Assalamualaikum and good day to panelists and lecturers. My name is AMIRUL SYAZUAN from 4SMMM. Today I would like to present my undergraduate project, which title is Perkins Brailler Actuator System, supervised by PMIR Dr. Muhammad Zarhamdy bin Mohd Zain. Before I start my presentation, I would like to apologize for any disturbance or noise coming from this presentation. For this presentation, there will be 5 chapters that I will be covering. The first chapter will be Introduction. The second chapter is Literature Review. Chapter 3 is Methodology, then Result and Discussion, and lastly, Conclusion and Recommendation. Chapter 1. For the introduction, in the early of the 19th century, the Braille was invented by Louis Braille, which is who is also a blind. It is a system for writing and a medium for communication for the blind worldwide. The invention of Braille transcribing system has improved the reading and writing amongst the blind people. One of the examples is Perkins Brailler, which allows faster and easier way for the blind to write in Braille. Standard Perkins Brailler is the first Perkins Brailler invented by David Abraham in 1951. It weighs about 4.8 kg. It is a fully mechanical brailler that has 6 keys to emboss the braille. It is durable and cheap, thus making it the popular in market. And this is the braille dot formation specification from the American Library of Congress. This is the Braille alphabet code from the American Library of Congress. The second one is the Smart Brailler, which is invented by David S. Morgan in 2011. The mechanic system is the same as the standard Perkins Brailler, but it requires less force to press the keys, as some mechanical parts are replaced with electrical components. It weighs about 3.8 kg. Smart Brailler is perfect for educational, as it has audio feedback, visual feedback, and can store and transfer data via USB. And this is the comparison between the Perkins Brailler and the Smart Brailler. Problem statement of this project. So the Perkins Brailler is heavy for the blind people to carry, which weighs about 4.8 kg. The Perkins Brailler also is expensive, which costs Rm 3,400. It requires high force to type the braille keys. Okay, for the objectives, it is to develop the prototype of Perkins Brailler actuator system, which can reduce the weight of Perkins Brailler, reduce the mechanical linkage of Perkins Brailler, and develop simpler design and system than Perkins Brailler available in market. The scope of this project is the study of the performance of Perkins Brailler actuator system, the design of a simpler and functional actuator system, the test of the performance of actuator system on a 140 GSM and 80 GSM paper, the evaluation and validation of the result. Chapter 2, Literature Review. From Jenkins and M, from the analysis of the Braille writer using asymmetric design, I have learned the use of pneumatic actuator in the Braille writer. For Ule MD, with the title of Low Cost Compact Braille Printing Head for use in a handheld Braille transcribing device. For this literature review, he used the linear actuator system for his Braille. The third one is Johnson H.A. with the title of Design of a Precise, Affordable, Brailleable Marker for the Blind. In this literature review, he used the FRD-PA-RRC, which is Functional Requirements Design Parameters Analysis Reference Risk Countermeasures, and SCMC, Strategies, Concepts, Modules, and Components, to provide a framework for the design and integrate ergonomic mechanism of the design. The fourth is Mohd, with the title An Electronic Design of a Low-Cost Braille Typewriter, which he introduce the erasing function for the braille. And this is my pattern actuator design. For the first one is use servo motor which connected to shaft with ram. The second one which use solenoid as a actuator system, and the third one is the Perkins Brailler, which is fully mechanical, making it complex. For the third chapter is methodology. So this is the flow chart of my project. The second one is the product design specifications. There are 4 criteria that is important for the product. The first one is the performance of the brailler, which capable of embossing braille dots on a paper, able to move from cell to cell, light and compact for portability, voice output system for educational purpose. And the second one is target cost, which should not be more than 500 ringgit. And the marketing is for the home user or self-teaching of braille, schools for the visually impaired and blind, and visually impaired and blind association. The last one is size and weight restriction, which the size of the brailler must not be more than 37 cm length, 23 cm width, and 15 cm height. The weight also must be not more than 4.8 kg. Okay, this is the functional decomposition block. First one is the push button, then next alphabet process, then actuator system, and the lastly embossing pin. So the morphology chart is made to give guidelines in designing the concept design based on the before function decomposition block. So this is the conceptual design that I have made. The first one uses solenoid, the second one uses servo motor, and the third one uses rack and pinion. So from the evaluation matrix, there will be 3 different persons for better evaluation of the design. The evaluation will focus on 7 criteria, which is embossing force, simplicity of system, ergonomic rigidity, troubleshoot, easy to install, and affordability. Design 2 wins the evaluation with the score of 131, and the design 2 will become a datum. Some improvement on the design will be made on the design 1 and 3, but design 2 still wins the evaluation, and this is the final design concept. Okay, the initial design embodiment of the final design concept will consist of servo motor connected to shaft with ram. It's the most vital part to emboss braille dots. The second one is housing base, which acts as a base for the housing and actuator system. The servo motor will also be placed at this base. The third one is the actuator housing, which are for protecting the embossing pin and holding the embossing pin. The fourth one is the embossing pin, which is very important in forming braille dots on the paper. Next one is the design failure mode and effect analysis. From the table, you can see the sections of the embodiment of the final design, which shows the failure mode, failure effect, and the remediation that needs to be done. Next is the comparison of motion of actuator system. As you can see, when the key is pressed, the shaft will rotate to drive the embossing pin. The system are all in mechanical linkage, which requires high force to push the key. And the second one is the final design concept motion, which shows the motion of final design of the actuator system. The shaft will rotate in an angle powered by servo motor to drive the embossing pin. Next is the chapter 4, result and discussion. And this is the actuator system prototype, which some modifications and improvements are made based on the evaluations before. Embossing head is added to the design so that to shape the braille dots and hold the paper. This is the Brailler prototype, which is the assembly of actuator system and Brailler prototype frame, which include the lead screw, stainless steel rod, bearing, and stepper motor. Okay, next is the assembled Brailler prototype, which is assembled with electronical parts with my partner Ari Shafiq. The mechanism is tested for design acceptance for the quality of the embossing braille. The Arduino Mega is programmed to provide output to the Brailler prototype. So there are Arduino. The electrical parts that is assembled is Arduino Mega, backboard, speaker, and other electrical components. So the steps are: when the keys are pressed, the servo motor will rotate the shaft and ram to raise the embossing pin. Then the pull motor with lead screw will move to the actuator system from cell to cell. The speaker will also activate according to the Braille alphabets. This is the motion of the mechanism of the Brailler prototype. From the results, we can see that the Brailler prototype cannot form braille dots on the 140 GSM paper due to low embossing force. But in the 80 GSM paper, the braille dots formed are not consistent and low quality. It is due to the mechanism of the actuator system that's not performing well, as the embossing pin spring tends to get stuck to each other and causing the embossing pin to not return to its original position. The servo motor is also underpowered, which has a torque of 0.1765 Nm and embossing force of 8.15 Newton. Then the cost analysis. From the table, we can see that the total cost is 460, which we have achieved the target of the product design specification, which is below 500 ringgit. For the weight analysis, we can see from the weight scales, the Brailler prototype is about 2.05 kg, and the weight is the target weight is achieved too. Discussions. The Brailler prototype is still indicated and needs some improvement due to the low embossing force and the design of the embossing pin that tends to get stuck. Nevertheless, the manufacturing cost is about 460 ringgit, which is affordable and reasonable for people to own, and the weight of the Brailler is 2.05 kg, making it lightweight and portable. Chapter 5. Conclusion and recommendation. So the conclusion is, the objective of this Braille prototype has been achieved, which is lightweight, simple mechanism, and affordable. It manages to optimize electrical components by replacing the mechanical linkage of the actuator system. Some improvements also must be done and fixing, so that the braille dots can be formed with high quality and consistently as it interacts with the user in order to aid the visually impaired and blind community. So the recommendation for this project is the concept design needs to be improved in terms of precision ergonomics so that the system can run smoothly. The second one is the servo motor, which needs to be larger and powerful, but it also makes the actuator system becomes more larger and becoming more expensive due to high power and larger. But integrating the system would simplify the design of the embossing pin and eliminate the need of spring. And this is the milestone of the UGP2. This is the reference that I have used. Thank you.